Space is defined by its silence, its emptiness, and its absolute, unyielding darkness. For millennia, humanity looked up at the night sky and marveled at the light. The stars, the nebulae, the blazing galaxies scattering across the cosmic void. But true astrophysics isn't about the light. It is about the dark, the spaces in between. The regions where matter gets crushed into a point so infinitely dense that reality itself simply gives up. We call them black holes. And for nearly a century, they were supposed to be the simplest, most elegant monsters in the universe. According to the foundational laws of physics, a black hole is a cosmic one-way street. Matter falls in, and absolutely nothing comes out. Not radiation, not information, and certainly not light. The boundary of this point of no return is known as the event horizon. To cross the event horizon is to leave the observable universe forever. It is the ultimate curtain, the final horizon of reality. Once an object, a star or a photon of light, slips past that invisible mathematical line, it is dragged inexorably toward the center, the singularity, a region where density approaches infinity and the laws of relativity and quantum mechanics completely break down. For decades, we were comfortable with this terrifying but predictable model. We believed we understood the anatomy of the abyss. We knew that supermassive black holes anchor the centers of almost every galaxy, including our own Milky Way. We knew that as matter falls toward the event horizon, it forms an accretion disk, a superheated, violently spinning ring of gas and plasma that glows with unimaginable friction, emitting X-rays and ultraviolet light. We captured the very first image of a black hole's shadow in the galaxy M87, and later in our own Sagittarius A star, confirming Einstein's general theory of relativity down to the smallest decimal point. The model was perfect, the universe made sense, the dark remained dark. But then we deployed the James Webb Space Telescope. We built the most sensitive, complex, and powerful instrument in human history, equipped it with hyper-advanced infrared sensors capable of peering through the thickest curtains of cosmic dust, and we aimed its golden mirrors straight into the darkest regions of space. We didn't just want to see the accretion disk. We wanted to look as closely as physically possible at the event horizon itself. We wanted to stare into the void. And the void stared back. In late 2024, during a prolonged and highly targeted observation campaign, the James Webb Space Telescope locked its near-infrared camera and mid-infrared instrument onto an active supermassive black hole situated at the heart of a distant active galactic nucleus. The initial telemetry looked exactly as the models predicted. There was the chaotic, turbulent accretion disk, glowing brilliantly in the infrared spectrum as stellar material was ripped apart by tidal forces. There was the photon ring, a delicate, mathematically perfect halo of light permanently trapped in the extreme gravitational curvature just outside the point of no return. And there, in the center, was the shadow, the absolute black, the region of zero emission. For weeks, the telescope gathered data, stacking exposure after exposure to create an image of unprecedented resolution and depth. But as the data processors at NASA and the European Space Agency began to filter out the noise and align the images, something completely impossible emerged from the numbers. The data did not match the theory. The standard model of astrophysics dictates that the interior of the event horizon must be utterly devoid of outgoing electromagnetic radiation. But the James Webb data showed a signal, a distinct, highly concentrated, and impossibly energetic emission originating not from the accretion disk, not from the glowing jets of plasma shooting from the poles, but from dead center. Right at the event horizon. Right where absolute darkness is mandated by the fundamental laws of nature. Let us be absolutely clear about what this means. This wasn't a smudge on the lens. This wasn't a glitch in the MIRI sensor array, and it certainly wasn't an artifact of the image processing software. The anomaly was verified across multiple observation wavelengths. It was real. Sitting exactly at the boundary of the event horizon, James Webb detected a highly structured, pinpoint emission of energy, an impossibly small, intensely bright focal point that defies every single equation we use to understand the cosmos. To understand why this is causing a panic in the theoretical physics community, you have to understand the rigidity of the rules this anomaly is breaking. General relativity is not a suggestion. It is the geometric framework of space-time. When a massive star collapses, its gravity becomes so intense that the escape velocity exceeds 300,000 kilometers per second, the speed of light. Since nothing can travel faster than light, nothing can escape. The event horizon is a mathematical membrane that separates the known universe from the unknown. If light is originating from exactly on or just inside this boundary, it implies that our fundamental understanding of gravity, light, and space-time is not just slightly off, but profoundly, fundamentally broken. Now, when astrophysicists talk about radiation in black holes, the immediate thought goes to Stephen Hawking. In 1974, Hawking proposed a revolutionary theory that black holes are not completely black. By combining general relativity with quantum mechanics, Hawking calculated that empty space is never truly empty. At the quantum level, pairs of virtual particles are constantly popping into existence and annihilating each other in a fraction of a nanosecond. If this happens exactly at the edge of an event horizon, Hawking theorized that one particle could be sucked into the black hole while its partner escapes into space. Over billions of years, this escaping stream of particles, Hawking radiation, would cause the black hole to slowly lose mass and eventually evaporate. So, could this blinding anomaly detected by James Webb simply be Hawking radiation? The short, definitive answer is no. Hawking radiation is incredibly weak. For a supermassive black hole, the temperature of this quantum glow is billions of times colder than the cosmic microwave background radiation. It is essentially undetectable. It is a slow, quiet, microscopic whisper across eons of time. What James Webb found is not a whisper, it is a scream. The anomaly is localized, highly energetic, and emits a concentrated signature that is completely inconsistent with the random thermal emission predicted by Hawking. This brings us to the terrifying question that physics currently cannot answer. If it is not the accretion disk, if it is not relativistic jets, and if it is not Hawking radiation, then what exactly is shining at the edge of the abyss? Several radical theories have been violently thrust to the forefront of cosmological debate. The first is the firewall hypothesis. For years, quantum physicists have wrestled with the black hole information paradox. Quantum mechanics dictates that information about the physical state of a system can never be permanently destroyed. But if matter falls into a black hole and is later evaporated as random Hawking radiation, that information is lost forever. To resolve this paradox, some theoretical physicists, known as the AMPS group, suggested that the event horizon isn't a smooth, invisible crossing point, but rather a blindingly hot wall of high-energy quanta, a firewall. According to this theory, anything falling into the black hole burns to a crisp the moment it hits the event horizon, thus preserving the information on the outside. Until now, the firewall was considered a purely mathematical construct, a desperate attempt to patch a hole between relativity and quantum mechanics. But the James Webb data might just be the first empirical evidence that the event horizon is not a dark threshold, but a violent, glowing frontier. Another, even more disruptive theory suggests that we are not looking at a black hole at all, but a massive gravastar or a boson star. These hypothetical objects exert extreme gravitational pull, just like black holes, but they do not possess a singularity or a true event horizon. Instead, they are hyper-dense spheres of exotic matter that might, under specific conditions, emit the exact type of concentrated energy signature James Webb has detected. If the supermassive objects at the center of galaxies are actually gravastars, then singularities, the points of infinite density that have plagued Einstein's equations for a century, might not exist in nature. The universe might have a built-in mechanism that prevents the creation of infinity. But perhaps the most unsettling hypothesis is that the anomaly represents a tear in the fabric of space-time itself. The extreme gravitational environment near the event horizon could be forcing higher spatial dimensions to intersect with our own. What we perceive as a pinpoint of anomalous light might be the geometric shadow of a four-dimensional structure, or energy bleeding over from a parallel membrane of reality. We are staring at a phenomenon that forces us to question whether our three-dimensional, linear understanding of time and space is merely an illusion, a localized rulebook that gets completely rewritten when exposed to the ultimate extremes of the cosmos.
What does this mean for the future of cosmology?
Everything. We are standing at the edge of a paradigm shift as significant as the transition from Newtonian physics to Einstein's relativity. For 100 years, we have built our understanding of the universe on a set of mathematical foundations that told us black holes were simple, dark, and final. We wrote textbooks, mapped galaxies, and predicted the ultimate heat death of the universe based on these assumptions. The data coming back from the James Webb Space Telescope has taken a sledgehammer to those foundations. The standard model of physics is officially on life support. We now have observational proof that the extreme gravity wells of our universe harbor mechanisms, energies, and structures that we do not have the math to explain. We are forced to go back to the chalkboards.
We need a unified theory of quantum gravity, and we need it not as an elegant thought experiment, but as an urgent necessity to understand the literal data on our screens. As the James Webb Space Telescope continues its observations, adjusting its focus to lock deeper onto this impossible light, the scientific community is holding its breath. We are waiting for the next data drop. We are waiting to see if the anomaly fluctuates, if it moves, or if it carries a spectral signature that could hint at the presence of entirely new particles or forces of nature. We built our most powerful eye to look into the darkness, fully expecting the darkness to be empty. We were wrong. The void is not empty. The event horizon is not a quiet grave. It is active. It is glowing. It is hiding something just beyond the veil of our comprehension. We stared into the black hole, expecting nothing, and the universe answered back with a light that changes everything.